Welcome to part 2 of the Comp 411 highlight reel. We've just finished talking about stacks and procedures and all the details regarding instruction set architectures, and now we're going to go a layer deeper into the physical layer. So here we can see the diagram that we saw at the very beginning of the course, and it goes over the different layers of abstraction we have. We finished talking about the compiler and the assembler linker, and now we're going to talk about how these are implemented on a hardware level with the CPU and all of its individual components. So one of the motivating factors for our hardware design is this idea of binary. We talked about binary in the lecture about encoding information, and in this lecture we're going to talk a little bit about how it's actually implemented. In the real world, it's implemented by sending some sort of voltage, and it's going to be either high or low. And this is because if we send a high voltage, we'll know what we really mean is a 1. If we send a low voltage, we'll know what we mean is a 0. But we have a little bit of variation between the high voltage, i.e. there's a range of high voltages that will allow to mean a 1, and we have a range of low voltages that will allow to mean a 0. And that's because you can't guarantee that you're always going to send the same voltage every time in a physical system, but if you allow a range, then you're able to get a certain value out each time, and it'll be the value that you expect it to be. There are two types of digital components. There are combinational ones in which the output only depends on the current input. An example of this would be an AND gate. You have two inputs, and only these two inputs are what contribute to the output. And then you have output where it's dependent on the past state, and this is a sequential component. In other words, these ones can hold state and remember their past, and they allow us to build memories. We're not going to talk about it in this particular lecture, that comes later, but an example of this is a latch, where we have a selector indicating where we want to read new inputs through here, or if we want to read the existing output and save it for later. This slide indicates all of the things that we need to have a combinational component. So you have to have one or more inputs, one or more outputs. Note that it says digital inputs or outputs, so that means a binary 0 or 1, and these result from some sort of physical voltage, as we talked about before. And we have to have a functional specification detailing the value of each input for every possible combination of valid input values. So that means that for every input value combination, you have to know what output you're going to get. And in practice, we can logically show this via a truth table, for example. And we also have to have a timing specification that has at least an upper bound propagation delay time. And this is the time that the circuit will take to produce the output value when stable valid input values are applied. This slide goes into the whole idea I talked about, where we have a max voltage representing a 1 and a minimum voltage representing a 0. So here we can see that we have a certain range of voltage, where if we have a voltage coming into our system, we're going to know that we mean 1. And if we have a value within this range of minimum voltages, we'll know that what we mean is 0. So 0 is represented by minimum voltage, 1 is represented by high voltage, and the same system will have to use the same voltage representation throughout. And note that there is a range of values in between your high voltage and your low voltage that simply does not translate to a 0 or 1. It's going to be too close to call, and your physical system is not going to know whether you meant a 0 or a 1. Some digital processing elements occur so frequently that we give them special names and symbols. So these are all different kinds of logic gates, and they'll do a very specific thing that's well specified with our inputs and outputs. So the ones we have on this slide here are the buffer. All it does is it has A come in and A comes out as well. There might be a little bit of delay in here, and sometimes that's desired, but that's what this does. We have an inverter, which will send the inverse of A out. So if we have a 0 in, we'll get a 1 out, and vice versa. We have an AND gate that does a logical AND between A and B. And I like to think of the AND gate as looking like a little popsicle. If you have trouble thinking of which ones you need to draw when it comes to drawing diagrams, that's how I remember it. And then you have the logical OR. This does logical OR, and I like to think this looks like a spaceship. And then you have XOR, which does logical exclusive OR. That is, if A and B are different, so A is 0 and B is 1, then you get a 1 out. If A is 1, B is 0, you get a 1 out. But if the two inputs are the same, then you get a 0 out. So these were logic gates that we saw, but they are actually consisting of something smaller than that, and those are transistors. And the most common technology for that we use is CMOS. And a CMOS circuit is what ends up giving you something like a logic gate, but it consists of a system of all these transistors. A transistor is just a switch that's either going to be open or closed based on whether it has high voltage or low voltage. And there are switches that react differently depending on what kind of transistor it actually is. So you have an N-type transistor called NMOS, and these switches are on, or they conduct, in other words, when the control input is 1. And then you have P-type. These switches are on when the control input is 0. Of course, N is for negative, P is for positive, and you use both types of switches or transistors together to build useful gates. This diagram shows in what situation an NMOS transistor and a PMOS transistor will conduct. So here we can see that for an NMOS transistor, the voltage is going to be conducted once we have a 1 input for that particular transistor. And for a PMOS transistor, we have conduction when the control input is 0. And this little circle here is what indicates that for PMOS, so because we have a 0 allowing the current to flow, that's sort of an inverter, and inversion is kind of negative. And so that's why you have a little 0 here, is to indicate that. So in order to make a CMOS system or one of these logic gates, what you really need is a system of PMOS transistors in a pull-up network in conjunction with NMOS transistors in a pull-down network. And when you build these systems, the pull-up network and the pull-down network are pretty much going to be logical complements of one another. That is, if you have some two transistors in series in the pull-up network, they're going to be in parallel in the pull-down network. And we'll see a little bit more of that in a second. The PMOS and NMOS networks have corresponding transistors. So if you have a transistor that we call A in the pull-up network, we're also going to have one that we call A in the pull-down network. And we're going to have an input going into both of them, and that input is going to be the same. So if you're sending a 1 into the A transistor in the pull-up network, you're also going to have that in the pull-down network. And on a physical level, we have one key difference between the pull-up and pull-down network. The pull-up network is going to have a source of voltage, and the pull-down network is going to have a voltage drain at the bottom. And what this does is, for the NMOS network, the drain is going to pull output values down to 0, and the PMOS network at the top is going to pull output values up to 1. Only one of the two networks conducts at a time, otherwise you're going to have undefined output. But by having two of them, it allows us to ensure that any combination of inputs that we do is going to be valid for the particular network that we've created. And here we have just a little bit more of that topology that I talked about earlier, where we have voltage at top, ground at bottom, and all the inputs in conjunction with this voltage and the ground will lead to a particular output, and that output is going to be 1 or 0. And on a physical level, you only have one of the two networks conducting at a time. Alright, and here we see a little bit the difference between the two networks. Over here we have a NMOS transistor, and as we noted before, it's going to conduct when the input A is high, and here we have our PMOS transistor. It's going to conduct when A is low, and we can use these together to create a sort of physical interpretation of a logical equation. So here we can see that when A is high and B is high, we're going to allow conduction to happen. And the way I like to think of this as because this is a NMOS connection, we have the ground down here and the output is going to come up here. What I like to think of it as is, well, can we actually get through A and B if we allow some voltage to come all the way up through here? So in other words, is the gate going to be open while for this connection while it tries to travel up to the output? On a physical level, that's not really how it works, but I think it's a useful heuristic when it comes to solving these problems. So basically, if you can get through B, you can get through A, you'll be able to get out. Similarly, we have parallel P connections, and because it's a P connection, it has this inversion here, and so what this represents physically is not A or not B, which is equivalent to not A and B. So, yeah, not A and B. So basically for this one, what we have is we're going to allow things to travel through if we have either not A or not B. And then we have something quite similar. We also have parallel N connections, which conduct when A is high or B is high. And we have these series PMOS connections that conduct when A is low and B is low. Alright, so let's look at one of these two input logic gates. So something that kind of trips people up about this slide is they see that there's only one input here, and it leads to both the pull up network and the pull down network. That's how things actually work in practice, but people tend to be used to seeing a distinct pull up and pull down network. So I'll show you how you would end up drawing this if you were to do it in a way similar to how you did it in the homework problems earlier in the course. So we start with our pull-up network. You can see in this diagram here that our P1 and P2 transistors are in parallel with one another, and that's just what we'll do here. And I'll label this one transistor 1 and this one transistor 2. Since this is a pull-up network, we have to be connected to our voltage, and as with any kind of CMOS network, you have the output coming out between the pull up and the pull down network. Alright, now let's draw the pull down network. You can see we have two NMOS gates in series here, and we'll do it just the same. And we can label this one 1 and 2, and we have our ground as the bottom, and this is now a different way of interpreting this network that we have here. The only difference is that we have two distinct inputs for our transistor 1 and our transistor 2. Note that in practice it would look like this diagram where we have some input 1 going into this one, and some input 2 going into this one and this one. And this is the truth table for that all. Well, I guess there's no truth table. We have to look at the next slide to see that. This is actually a different slide than the next slide that was originally on the presentation, but we can see here that you can make these circuits, these networks, with an arbitrary number of inputs. And here we have a very similar circuit to the one we drew before, except for it's a NAND, and it's going to be accepting 3 inputs. This slide indicates that CMOS gates always invert, so if all the inputs are 0, the output's going to be a 1, and the path goes through the P transistors. If all the inputs are 1, then the output's going to be 0, and a path is created through the N transistors. Sorry if my explanations on transistors weren't the best. It's by far the topic in this class that I'm the least comfortable with, but if anybody wants, I can look into it a little bit deeper and maybe make a video on the CMOS gate problems, because I do know how to do those. Anyways, next we're going to look at gates, Boolean algebra, and synthesis, and this is going to be a level of abstraction above our transistors, so we can piece together transistors to make gates that represent logical operations. Some of them are not. Not is a simple inverter, which will take the input of A and do an output of Y that's just the opposite binary bit. For a buffer, we will simply output exactly what we put in. It'll take a little bit of a delay to get from one side to another, and sometimes this is a useful behavior, but you can think of it as something that just puts out what you put in. We have two input logic gates, and these are the most basic logic gates and probably the Boolean operators you're the most familiar with. There is and what that one does, of course, is it sends out a 1 only if A and B are both 1. We have OR, which will send out a 1 if either one or both of A or B is 1. And then we have more two input logic gates. We have exclusive OR, which will send out a 1 only if A and B have different values. We have NAND, which will be a 1 only if the value is not A as 1 and B as 1. So basically the opposite of NAND. So basically you can see here that all it is it is a inverter following an AND gate. We have NOR, which is also the same, pretty much, same idea. You have an inverter following an OR gate. And what this does is you have a 1 only if both of the incoming values are 0. Otherwise, you'll have 0 come out. And then you have exclusive NOR, which is a inversion of the XOR. And you can extend the same idea by adding more transistors and simply extending the behavior of the gates we had before. We have NOR but with 3 inputs, and what this does is it sends out a 0 if any of the inputs is a 1. So it will only have 1 for the output if all the inputs are 0. We have AND 4, which takes 4 inputs and only sends out a 1 as the output if all 4 of the inputs are 1. So not all basic gates can be implemented using a single CMOS gate, but some can be. It's our inverter, NAND, and NOR, and that's because, as we saw in the transistors lecture, these gates are sort of naturally inverting. But if you invert inverter and chain 2 of these inverting gates together, you can result in some sort of behavior like AND or OR. And as you can see here, AND is implicated with a NAND followed by an inverter. OR is implemented with a NOR with an inverter. A buffer is implemented with 2 inverters. And we'll take a look at XOR and XNOR later, perhaps. Alright, so now that we see that we can have these gates where you have certain inputs reduced to 1 output, let's see what we can actually accomplish with that. Here we have our Boolean identities, and I'll just walk through these quickly. So if we OR anything with X, you're going to get X, so X meaning some value of a bit, either 0 or 1, could be either. It'll just preserve its original value. And as far as notation is concerned, we have this plus sign indicating an OR, and this dot sign indicating an and this line indicating a NOT. So we'll walk through these real quick. Number 1, as I said, means that any value ORed with itself is that value. Any value ANDed with 1 is that value. Any value ORed with 1 is 1. Any value ANDed with 0 is 0. Any value ORed with itself is itself. Any value ANDed with itself is itself. Any value ORed with the complement of that, so all the bits inverted basically, is going to be 1. So we can take a look at that. Let's say we have binary 1001. If we take a look at binary not this, so if you put a big old not over this, it'll invert everything, and we'll get 0, 1, 1, 0. Sorry, I meant to do an OR sign here with the 2 tall lines, but that's a little confusing because they look like ones, so I'll do this instead. So 1 and 0 equals 1, 0 and 1 is 1. As you can see, you're going to end up getting all ones, which is what identity number 7 is saying. And the identity 8 works very similarly, except for if you AND value by its complement, you will get 0. And then if you do the complement of a complement, you get the original value itself. Note that I use the terms complement and not interchangeably. Commutativity is simply the idea that some operations are going to be independent of the order of variables, and this is basically exactly how things look in your arithmetic and multiplication that you learned in elementary school. So nothing revolutionary here. X or y is the same as y or x, and x and y is the same as y and x. Associativity, in this case, the order of the values is going to be independent of these parentheses. In other words, where you put the parentheses doesn't matter. So you could group the parentheses around y and z here, or x and y, but they're both going to mean the same thing. In either case, what we are really going to end up getting is x or y or z. And similarly for this identity, x and yz is the same as xy and z, which is simply x and y and z. Distributivity is the only one that I think looks a little bit weird. For this one, we have our sort of multiplicative distributivity, and this looks very much like the distribution that we saw in elementary school, where you multiply this by this and you get x, well, what looks like x times y plus xz, or x and y, or xz, and all is good with that. But this one, number identity 15, looks a little bit strange. So we have x or yz. Well, we get that what is equivalent to that, given the identity, is x or y and x or z. And this might seem a little confusing to you because it seems weird that you would distribute this x, because this looks like an addition sign, but it's not exactly addition. And so if this looks a little bit strange to you, I encourage you to write out a truth table for the x or yz and the x or y and x and z. Here we have De Morgan's theorem, and this is basically the idea of kind of inverting a Boolean expression. So the way we accomplish that is we sort of distribute the not that we have over an entire expression, and we put it over the individual pieces, and all of the ors will get flipped to ands and vice versa. So that's what's going on here. And in practice, if you were to implement this, you would have a NOR or a NAND gate. And so here you can see this is just an OR gate with an inverter at the end, so NOR. And here we have a NAND gate, so an AND gate with a inverter at the end. So this NOR gate is equivalent to a, let's see, this is an AND gate with the individual inputs inverted, and that's what we have going on over here. So once again, if you just work out the truth tables for them, you'll see that they are in fact equivalent. We can use algebraic and Boolean identities to simplify expressions. And so here we have a logic gate sort of path that leads to one output in particular. So first, let's just trace where all these variables are going, because this diagram is kind of confusing to read. But we'll note that, so we have our first expression, and this corresponds with this gate right here. Not x and y and z is going to generate a 1 if these inputs are given. So let's look at the input x. We'll see that it follows the path from here, the y follows the path into here, and the z follows the path into here. So note that the x gets inverted and the y and the z do not get inverted. So if those are all the way that they're described in this expression, then it'll come out as a 1. And then you have something very similar going on for all the other gates. And basically what happens is the result gets ORed at the end, so if you have any one of these inputs come out as 1, the entire result is going to be 1, because you're doing that whole OR operation. But there's actually a more simple way to express this and also draw the gate than the way it is here. You could simply do it as f equals not xy or xz, and you can see that this represents the same truth table as we had before, but it makes use of way fewer gates. This one had 2 inverters, 3 AND gates, and an OR gate. This one has 1 inverter, 2 AND gates, and an OR gate, so it looks like we saved 2 gates here. Let's look at how we actually go from a truth table to generating a circuit of gates. So what we start with is a functional specification. We want to ask ourselves, for what inputs will we get a certain output? And we need to do this for every possible combination of inputs. And the way you do this is you draw a truth table. The convention is for the each of the inputs, you'll start with having all zeros, then you'll have 0, 0, 1, 1, 0, 0, 1, 1, then 0, 1, 0, 1, 0, 1. This is just a convention. It's easy to draw out your truth tables quickly that way. But all you need to do is, once you do that, you'll have every combination of values for each of your inputs, and you then decide which output is going to be generated for each input. So for this example we have here, we see that if C is 1, then we copy B to Y, otherwise we'll copy A to Y. Well, let's look at what's happening there. If C is 1, we copy B to Y, otherwise we copy A to Y. So for all of these so for all of these ones here, C is not 1, so we simply copy A over to Y, and you can see this happening. All of our A's are corresponding to Y for those outputs. And then if C is 1, we copy B to Y. So let's look at that. Here we can see those corresponding with one another. So you can see we start out with a sort of text interpretation of what it was we were trying to make, and then we actually made it by use of a truth table. And this is the design approach you'll make before you make any sort of CMOS or logic gate circuit. How many gates do we really need? Well, we've kind of mentioned before that NANDs and NORs are universals because you can just chain NANDs and NORs together and it'll end up inverting it so that you get regular AND or OR, and as a result you can get any combination of gates that you need. Some gates have more than 2 inputs, and the way you would normally do that is construct it using smaller gates. For example, let's say we want to have a 3-input AND. What we could do is we could have something like this. Right, so we have an AND gate here with the output coming out here. And then you would have the output of that going into our next AND gate, and then our third input going into here. Because ANDing is associative or commutative, one of those, it ends up working out just fine. And if you decide you want to end up chaining them together like you have here, you would have A0 and A1, then you have an additional input coming in here, additional one coming in here. So basically you have a new input each time, and you're also taking in the ANDed product of the old inputs so far, which we can do because, as we mentioned, AND is commutative. You could do them in any order, and so this basically allows you to have multiple AND inputs, and we're going to have a sequence of AND gates. And the number of AND gates you end up having is n-1, it seems. As a result, the delay in computing the final output is linear in the number of gates. It's going to be big O of n, which means it's on the order of magnitude relative to the number of gates we have. So the number of gates we have will grow in proportion to the number of inputs. Let's look at how we sort of go the other way around, develop a Boolean equation in response to a truth table, because what we've seen already is how to develop a truth table based on some kind of text interpretation, but we'll kind of go backwards and see what we can do once we have a truth table. The approach we have is called sum of products. So we start out with a truth table, and what we do is we look at each of the outputs where the output is 1, and then we look at the corresponding inputs. So For this one, we would say, okay, we have not C and not B and A. That's what this represents. And then another one we have is not C or B or A. That's what this one is. So basically, if any of these inputs, if any of these combinations of inputs are going to be sent in, then you'll get 1 as the output. And the idea you have here is you could have each one of these products that results in a positive output, or an input of 1 rather, and then you just OR all of these together. And that is what's going to give you your particular Boolean expression that you need to make circuits representing with logic gates. And this approach is called sum of products because each of these combinations is a product because you're ANDing all these together, and then you're ORing all of these products together, so it's a sum of products. And sum of products can be implemented with just 3 levels of logic. We need inverters, we need AND, and we need OR. So note that for each particular product, you end up ANDing all of them, so you need an AND gate for that. So here we have a 3-input AND corresponding to our not C and not B and A. You have to invert for the nots so that if you send in a not B, it'll end up getting inverted to a 1. So the AND gate will recognize that it'll send out a 1 if you send in a 1 for A, 0 for B, and 0 for C. And then it basically ORs the value of all of these AND gates, and if any one of them has an output of 1, then it'll send out a 1 for its overall output. Let's look at an interesting 3-input gate called a multiplexer. A multiplexer is something that is going to allow us to choose between different values, essentially. This is similar to the truth table we saw earlier. If C is 1, then copy B to Y, otherwise copy A to Y. Let's look at what's really happening here in the gate. So C we can think of as some sort of input signal that's going to signal whether we're going to copy the value of A or the copy of B. And that's exactly what's going on in this truth table here. So what's going to happen is first you'll look at the value of C. The value of C could be the value of, or the value of C could be 0 or 1. If the value of C is 0, you look at the input A, and if the value of C is 1, you look at the input B. This kind of trips up students sometimes because they'll think that if you send in a 0, then you get like a 0 out from A or something. It's important to note that the value of A or B can be any combination of bits. It's not necessarily going to be just a 0 because there's a 0 here. The 0 simply means if you send in a 0 for C, that's the input that you're going to look at, is the input A. And you can do a multiplexer with more than 2 inputs. What that will basically look like is instead of sending in 1 bit for the selector bit, you'll send in 2 bits. Basically, 2 bits is going to encode 4 different values. We remember how that works from our encoding information lecture. So for s equals 0, we could send in 0 and 0. For our S bits, and S1, S0 is basically going to be the number in binary corresponding to the input number of the gate sizes we want to look at. So for binary 1, 1, we see that we have S1 a bit of 1, S0 a bit of 1, and this will correspond to look at the third input. So you'll get D out in that case. And over here, what we have on the left side is really just an abstraction for what's actually going on. What really happens is you have 2 levels of logic here. So for example, let's say we want to get the value for s equals 2. If that's the case, then we send in a 1 for our, we send in a, we send in a, this is backwards. It was little confusing to me, so we'll send in a 0 for S0 bit and a 1 for our S1 bit. So what happens here? So for this, we are sending in a 0 to this multiplexer and this multiplexer. So that means that the values we end up have coming through are A, and C. So right now we have the value of A coming in here and the value of C coming in here. And then we look at the value corresponding with 1 as per this selector bit, and so the value of C comes out. And that's sort of the mechanics behind what's going on here. You can also have a multiplexer with 2 inputs, and in this case, the inputs themselves are more than 1 bit. So note that in these examples before, we had A, B, C, or D just representing 1 bit each. But in reality, if each of the inputs was more than 1 bit, what you would need is a separate multiplexer for each bit. But note that this works very similarly to how it did originally. You're just going to have more outputs. So for example, let's say we send in a 1 to our selector bit. It's going to propagate up here, 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 and here. And what you end up getting out is B0, B1, B2, and B3. So we got out all the bits of B. We just had to have a separate multiplexer for each bit, which is one design approach that we can do if we have multi-bit inputs, which we often will if we're dealing with numbers, for example. So we now know how to make logic gates, and that's great and all, but you might be thinking to yourself, when was the last time I had to do a logical AND or a logical OR? Well, as it turns out, this is what is going to compromise our ALU, which lets us do arithmetic, which you probably do on your phone or computer every day. So let's see how we can use these basic logic gates to do arithmetic and logic circuits. The way we do addition in binary is basically the same way we would do addition in decimal. You do the basic algorithm where you look at everything on the right-hand side, you add it, carry over if there's a carry, and then you add the next column. So in decimal, this is 21. I was thinking in binary for a second, got a little confused, but you can see the algorithm here is basically the same. 1 plus 1 is 0, carry over 1. 0 plus 1 is 1, carry over 0, since we're not carrying anything over. 0 plus 1 is 0, and so forth. And the way we implement this is with a circuit of these individual adders. And let's look at what is in one of these adders. So you're going to have each one of these adders take in an individual bit from A and an individual bit from B. So the first one it would be taking in would be these two. So the 1 for A and the 1 for B. And it also has to look at a carry in bit, Ci, because remember, once you get past the first column, you might carry over a value that you have to add to everything else. So ultimately, what you're going to do is you're going to add the values A, B, and C. You're going to get that out as your value S. And then if there's a carry value, you want that to carry over to the next adder. And basically what each adder is going to represent is the output for a particular bit of a number. So let's apply all of this to this example that we have up here and this cascade of adders that we have. So first we have to assign all the bits according to their inputs in the adders. So in this example, we have this as A0, this is B0, so we have 1 and 1. This is A1, this is B1, 0 is 0. And we'll just continue on here. And note that at the very beginning, we don't have any carry in. So what we have coming in here is simply a ground, because remember, a ground is going to transmit 0. So what we have here is 0 for Ci plus 1 for A0 and 1 for B0. So 1 plus 1 is going to give us 0 in binary, or rather 10 in binary, so we get a 0 because that is the rightmost bit, and then we carry out the 1, and when we carry it out, it becomes the carry in for the next adder. So now we have 1 plus 0 plus 0. That gives us 1 for our output bit, and we don't have a carry for this one, since there was no bit past the rightmost bit.
have a 0 as a carry in for here. 1 plus 1 plus 0 is 0. So we have a 1 for a carry out, 1 for a carry in on the next one. 1 plus 0 is 1. So we get 0 as the output and a 1 for the carry out. And then note that we have one additional spot here where there's no adder, but there is a space for the carry out. And that's because when you do addition, the most number of additional bits you can get is 1 more than the largest number of bits you have in either A or B. So that's how this algorithm works, and that's how we can implement it with adders. So now we have a truth table representing this whole thing. And the reason why we have a truth table is, remember how I was talking about how this whole thing is really just comprised of ands or ors? You don't get a sense of that for this whole box, because this box is just an abstraction for everything that's going on. But we'll see how we can actually implement it using gates once we look at the truth table. So someone who's smarter than I took a look at all the inputs, C, I, A, and B, and determined how you get C's out and S based on that. And they determined, doing the sum of products algorithm, that for outputs of 1 for C0, we can have not CI and AB and B, or yeah, not CI and A and B. We could have CI and not A and B. We could have CI and A and not B, and so on. And the same stuff applies for S. You simply look at the inputs here where the corresponding output is 1 for S, and someone figured out that you could simplify this to be what we have here. And if I read it out loud to you, it'll make sense. So for the carry out value, what we end up getting is the carry in ANDed with A XOR B or AB. So in the event that we have AB, that means that both A and B are going to be 1, and 1 plus 1 is going to be 0. 1 plus 1 is going to be 10 in binary. So you get a 0 for the S field and a 1 for the carry out field, and that's what this is saying here. Alternatively, you could have CI, so you could have a carry in, and then you could have A XOR B. So if you have a carry in as 1, and either the A or the B is going to be 1, then you end up getting a carry out in this event as well. And then simply look at your S value. So you have carry in XOR A XOR B. So what the S field is going to be dependent on whether we have a odd number of carry in A or B, basically. And you can see that corresponding in the truth table as well. Alright, so we've got that, and we can see now that since we can basically make this entire adder circuit based out of a combination of AND or gates, let's now see how we can do subtraction. So now we have subtraction. Subtraction makes use of the full adder the adder we had before, because it basically makes use of the property that A minus B is equivalent to A plus minus B. And we can get minus B by simply taking the complement of our B that we had and adding 1 to it, because that is how you get the negative version of a number using 2's complement. So what we want to do is we're going to add these XOR gates before we have the B input of each of the individual adder pieces. And what we're going to do is we have a sort of control flag coming in for subtract, and that's a 1 that's going to come in. So if we want to do subtract, we have a 1 coming in to all of these XOR gates. And allow me to show you the effect of that. So let's do a simple example where A is 1001, B is 001 as well. And what I'm hoping to illustrate is that when you do A plus minus b plus 1, what we end up getting is 0. So what we end up getting should be a minus b, which of course is 0 because these are the same. We'll send in all the bits for for b. And what happens is they all get XORed with 1. So 1 XOR 1 is not going to be 1 anymore. It'll get inverted, and so you get a 0 out of that XOR gate. For the 1 that's coming in here, it gets XORed with a 0. 0 and 1 will output a 1 for exclusive OR. And so you can see that what happens is with this 1 XOR input bit behavior we have with the XOR gate, it's going to always invert whatever bit we have from B that comes into it. So we finish this here. And we also send in the values for A as we would normally. So this gives us our B and our inverted B, but what about the plus 1? Well, remember we used to have this connected to a ground when it was just an adder, but now what we have is we have the 1, if we're doing subtraction, coming in here into the carry in field of the original adder module, the very first one in the sequence, and this will just add 1 to everything. So let's see what happens. We get 1 plus 0 plus 1 here. This gives us S0 as 0 and C0 as 1. Carry this over. We have 1 plus 1, since Ci is 1, B is 1, and A is 0. That's going to give us a 0 for S1 and a 1 for our carryout. So let's carry in a 1 for the next one. 1 plus 1 plus 0. Same thing. And we take that result again. 1 plus 0 plus 0 gives us 0 here. Carry out of 1. And we have a 1. And so we have a carryout bit here. But you can see that for the rest of them, we get 0, which was the expected result. Since we can do addition and subtraction now, we can also look at the result of when we do our addition and subtraction, and this will give us what's called flags. And so once we have done some sort of arithmetic operation, these flags basically will be the result of when you look at a certain feature of the result, and you're just going to determine is that true or not. So these flags are always going to be set to 0 or 1 based on whether the condition that the flag represents is true. So if the result of your arithmetic is 0, you'll have your Z flag set to 1, otherwise it'll be set to 0, and that can be simply implemented with a NOR gate at the end. You can have a AND gate for negative to see if the result is negative. And so if the result is negative, it'll be less than 0, and your N bit will be set to 1. And you have something similar going on for a carry bit that indicates that the most significant position produced a carry, as we had in our example just before. So in other words, in the example we just had, the C bit for carry would have been set to 1. And then we have a V bit for overflow. And the real utility of this is it allows us to find certain Boolean comparators between two numbers. So the way this works is you simply take A minus B, and based on that, you can look at the condition flags and find out a lot of information about these numbers in relation to each other. For example, if A minus B equals 0, then of course the numbers are going to be equal, because if you rearrange that at algebraic inequality, you just get A equals B. And so the Z flag is going to be thrown. It'll be set to 1 every time there is an equality in this sense. Similarly, if the Z flag is not raised, is not set to 1, it's set to 0, you'll know that the numbers aren't equal. And you can do similar things with the other condition codes. How long does addition take using one of these adders? Well, we note that at each one of these we need to get the carry out value of the one before it. I apologize, this slide rendered a little bit weird. All the CIs should be here, but basically the CIs needs to go to the COs need to carry over to become the CI for the next one, which means that each adder is dependent on the value of the carry out of the adder that came before it. So you need the time to propagate through every one of these adders, and that means you have a
time delay proportional in size to the overall number of bits it is that you're adding in your inputs. And so that's big O of n in other words. Alright, now we're going to talk about shifting and logical operations. So there are a couple different kinds of shifts. There's shift left logical, which does a logical shift and pads the right hand side with zeros. You have shift right logical, which will shift all the bits to the right and pad the left hand side with zeros. And you have shift right arithmetic, which will pad the leftmost side with either 0 or 1, depending on what the leftmost bit is, and it'll shift right, of course. And what it does is it looks at the leftmost bit and it determines, okay, is it a 0? If so, I'll pad with zeros. If it's a 1, I'll pad with 1s. This allows us to maintain the same number when it comes, or not the same number, but the same positivity or negativity when it comes to our 2's complement notation. And the way we implement our shifting logic is with a multiplexer. So what we have here is we have one multiplexer for each bit of the input. So let's say we have an input 1001, 1001. So you simply fill in each input bit, and then this is going to work the way a multiplexer always does, is you'll take a value either 0 or 1 and it'll propagate up through all the multiplexers since you have this going to each one of these. But let's say that the value going into the multiplexer is 0. What's going to happen is you're going to look at 0. For this first one, it's going to be x0. So, sorry, that's 1 because x0 is a 1. It'll come up here, look at what the 0 input is. It's x1. So if you're not doing the shift, you get the same value you got before. Well, this is pretty obvious. What happens if you send a 1 into the multiplexer? Something interesting is going to happen at the very first multiplexer we see. We get a 0 out. That's because with shift left logical, we're going to shift on the right hand side. When we shift, we pad the right hand side with zeros. And so we have 1 0 we have to pad because we decided to shift left. And now when we go up to the next one, what we're really doing is we're getting the bit from the position following it. So we're getting x0 to be in the R1 position. Same thing happens up here. You get x1 to go in the x2 position. And this carries all the way up. And so the end result is we get a left shifted value by 1. We can extend this notion of having multiplexers to select which bits in a number it is we exactly want, but instead of linking it to be just the bit going to the multiplexer above it, because that'd be for shift left 1. Let's say we want to do shift left 2. Well, you would have this going up to you'd have XO going up to R2, x1 going up to r3, and so on. And so note that by doing it this way, you can have an arbitrary number of bits that you shift by. The only difference in this case would be you would also need a 0 to be the input for 1 here if you end up shifting for SLL2. And if you do shift right, I forgot to mention, one thing you will have to look at is you'll have to determine whether your leftmost bit is positive or negative, and that'll determine whether you send in a 1 or a 0 here when you're padding. So I talked about how you can shift an arbitrary number of bits, but we don't have a shift left logical 3 circuit, for example. And the reason for that is because you can get any combination of numbers ranging from 1 to 31 if you have a shift left logical module for 1, 2, 4, 8, and 16. And that's all you need because the most number of bits you'll need to shift is 31. So with any combination of these, you can get any value of bits between 1 and 31 to shift by. And the way you'll process them is in order like this,
And so note that if we want to shift by value of 13, what the inputs end up looking like is binary 13. And essentially, this is what constitutes the shift amount field in our MIPS opcode. So that's just an example of how things are all starting to come together. Alright, what about a Boolean unit? So we know that we can use one Boolean function if we have a gate. But what if we want to be able to use multiple Boolean functions? We can make use of the same idea of a multiplexer here, where we have some two bits coming in indicating which Boolean function it is we want to do. And note that up here we have the inputs going to every one of these gates. We have here a AND, we have a OR, we have XOR, and we have NOR. And AI, so that's to say the ith bit of A is going into all of these, and the ith bit of B is also going into all of these. So that means that each one of these gates is generating an output, depending on what A and B is. But we actually only look at one of them based on what the selector gives us. So if we have 0 and 1 as our bits for the Boolean selector, we would get the result of AI or BI, and that would be our overall output. One thing to note is that this thing here is actually going to be 2 wires and corresponding to 2 multiplexers. This is just a way to make it easier to write down. And note that the cost of doing this is about 7 gates per bit. Okay, so now that we have each of those pieces, we can make a near-complete ALU that has the addition and subtraction module, the bidirectional shifter module, and the Boolean module. And what happens is you have your input A and B going into each one of these, and what you do is you simply put your control bits in, and those will go through a multiplexer that allows you to indicate which one of these operations is you're going to do. And the way you indicate these operations is with your opcode in your MIPS instruction. So for example, let's look at this. Say we want to do subtraction. Well, if we want to do subtraction, we want to send the subtraction flag into the add subtraction module, and we want to do math. And what that ends up doing is A and B will go into here. It goes into all of them, but that's the one we're concerned with. And you'll get the value of that out, and then you have a multiplexer here indicating that the math field is the math result is the one that we're concerned with. And when you do that, it ends up not mattering what the Boolean and what the shift values are, because we're not going to use Boolean and we're not going to use shift. Let's look at another example. Let's see what happens for A or B. So for this one, we want to use the Boolean module. You have A and B going in here, and you have to indicate which Boolean function it is you want to do. For OR, it's going to be O1. That corresponds with the Boolean circuit that we saw on earlier slide. And we also want shift and math to be set to 0 to indicate that we don't want them. And what that does is, at this multiplexer here, you have a 0, so that'll say, okay, what we really want is the Boolean value, and it'll come through here, and you specify math 0, and it'll let you get the Boolean value out here. And you're also going to have the condition flags being raised as well at the end when you get the result. So these bits where it doesn't matter what value it is because you don't use them are called don't care bits. You can send anything into them and it won't affect the result. And we have just one modification of this, and this is a complete ALU. It makes use of the flag results, and it lets us do our less than and our less than unsigned instructions, basically by doing these operations, and that gives us support for branches within our ALU. And that's it on the ALU. If you liked addition and subtraction, you'll love multiplication, division, and floating point, which are a little bit more complex algorithms that we can also apply using adders. First, let's look at the binary multiplication algorithm. It's basically the same as the decimal multiplication algorithm that you learned in grade school, where you look at the one bit from the bottom and multiply every digit from the top by that. So this is reflected here where we see we have A0, A1, A0, B0, A1, B0, A2, B0, and A3, B0 all over here. And then when you're looking at the next bit, B1, you do the same thing. You take each of these, A0, B1, A1, B1. You can see all these here, but it's shifted to the left one amount because this is a more significant digit here than B0 was. And each of these is going to be a partial product, and you just take the sum of them all, and you end up with your final result. So let's look at the actual inputs and outputs we have here. And what we were doing with them. So for A was pretty much staying the same each time. We just multiply each bit of that by B, the bit of B that we were looking at. But we need to know what bit we're looking at, and in particular when it comes to binary, we need to know if we're multiplying by 1 or 0, because if we multiply by 1, you're just going to get A, because A times 1, or A and 1, is just going to give you A, but A and 0 is going to give you 0. And here we have the overall algorithm. So the one that doesn't change, and the one that we're going to multiply by B, a bit of B at each point, is going to be a multiplicand, and we'll call that A. And then our multiplier B is the one where we look at the individual bits of them at each step after we finish multiplying each bit of A by the bit of B we were just multiplying by. And here we see how we have to implement this in hardware. So instead of doing all this stuff with shifting left, what we start off with instead is we dedicate half of a register to using the bits of scratch work, and then once we're done multiplying a particular column, we'll shift things over. And the reason for that is because once we are done with doing the first column here, you never add anything else to this particular bit, so it can stay put. And so the idea is that by the very end, you won't have anything in here anymore, and you'll have the product on your right hand side. So what we start off with is we start off with doing everything in the leftmost bits. We do a shift right and all that. It's a little bit easier to explain the algorithm with an actual example, but after I do the example, just look back at this flowchart and see if you understand it. The key things to make note of is that we look at one bit of the multiplier at a time. Right, with this being the multiplier here, we would only look at B0 or B1 or B2 or B3, and you'd have to determine whether this is a 1 or not. So we have to send this into some sort of logical operation indicating whether the bit we're looking at is a 1, and then if it is, then that's going to determine what we do with the multiplicand going in here. And we'll see how this all works in the algorithm here. Note that this is going to be a smaller scale version of what would actually happen in a real register. This is just to save time, but instead of having a 32-bit register divided into two 16-bit pieces, we are going to have a resultant product register that is just 8 bits. So we start off with a multiplier of 1011 in this example, and a multiplicand of 0010. So we note that the multiplicand is going to stay the same throughout. That's because it is the value that is on top. It is our A in the chart that we just saw. So let's look at the multiplicand now, or the multiplier now. So we see that the rightmost bit is 1. And so what we end up doing is we take the multiplicand times this bit. So 0010 times 1 is just 0010, and what we do is we add 0010 to the leftmost 4 bits of our product register, and that's because this is just one partial product that we're adding to the overall product. And then once you're done doing that, you shift the multiplier number to the right by 1, and you shift the product number to the right by 1, because we are done looking at that level of significance, basically. And so once we've done that, we repeat again. With our new shifted multiplier, we look at the rightmost bit, we see that it's a 1, and so what we do is we multiply the multiplicand 0, 0, 1, 0 by 1. This gives us 0, 0, 1, 0 again, which we will add to the rightmost, or the leftmost 4 bits of our product. And something to note is that in practice, the way you could actually implement such a thing, where you do addition, but you only do it in the leftmost 4 bits, is you could do some sort of anding or ORing operation, where you do something like you and where only you and something with 1, 1, 1, 1, 0, 0, 0, 0, so that the rightmost 4 bits are guaranteed to be 0, for example, but whatever bits you have for the leftmost 4, those will get transferred over. So we add 0, 0, 1, 0 to the leftmost 4 bits of here. You get 0, 0, 1, 1, because previously it was just 0, 0, 0, 1, and then we shift that over, and we shift the multiplier over again. We do our test again. We see if the rightmost bit here is 1 or 0. It's 0, so we add nothing to our product here. We simply do what we did in every case, which is we shift this right by 1, and we shift the multiplier right by 1. And now finally for the multiplicand, we see if this bit is a 1, and it is, so we add a 0, 0, 1, 0 to a 0, 0, 0, so we add 0, 0, 1, 0 to the leftmost 4 bits of our product, because that's what this times 1 is, and you end up with this. Shift each one to the right by 1, and you end up with all zeros here, and once the multiplier is full of just zeros, that's how you know you're done multiplying. And if we look at what we ended up getting, for the product we have 1, 0, 1, 1, 0, which will give us 2, 4, 16, so 22, and then what were our multiplier and multiplicand? Multiplier were 8 plus 2 plus 1 is 11, and our multiplicand was binary 2, so 11 times 2 is 22. So it works, and what we need for that to work in hardware is we need the ability to do logical shifts. We need the ability to control and see if the rightmost bit of the multiplier is actually a 1 or a 0. We need the ability to add to the product, and we need to be able to do the shifts within there as well. And that's do all that, and you have yourself a multiplier. And notice that for each iteration we have here, these iterations were happening in time, so we would have just one of these overall systems doing this bit of work, but we could have multiples of them, we could have more of them in sequence, so that instead of taking up cost in time, we are taking up cost in space, so because you are able to just send in the bits rather than wait on the outcome that you had before. Here we have a similar algorithm for division, but just the algorithm. Won't go into detail. If you want to understand it a little bit better, you can look at the book, but this is by far not the most important part of this lecture. Now we have floating point numbers in arithmetic. Floating point numbers, as you might recall from the information representation part of the class, is just another way of encoding numbers, and it lets us do fractional bits in a pretty interesting way. So floating point numbers are how real numbers are often implemented in real life, because they let us do a pretty cohesive range of fractional bits, as I mentioned, because with 2's complement, for example, we only had integers. You could do some sort of fixed point thing where you had 4 bits, and then you had a little decimal point here, and then 4 more bits, but there still is a pretty limited amount of bits that you can represent fractionally if you do that. But this will let us have a pretty large amount, and we'll see why. So first, we should note that scientific notation is somewhat similar to floating point in the idea that you have some sort of significand multiplied by an exponent. In this case, the exponent is a power of 10, but for floating point, the exponent is a power of 2. So we can see that 42 is simply, in scientific notation, 4.2 times 10 to the 1. 1024 becomes 1.024 times 10 to the 3, and minus 0.065 becomes minus 6.25 times 10 to the minus 2. So you normalize all of these numbers so that there is one digit and one digit only to the left of the decimal point, and then you encode the rest of everything. You encode its magnitude by multiplying by 10 to some power. And you can do the arithmetic in pieces. What you have to do is you have to normalize the numbers so that the numbers that you're adding or subtracting are on the same order of magnitude. And you get 42 on the same order of magnitude by moving the decimal point over some so that you can multiply by 10 to the 3. Then you can just subtract this value from this, and you're left with 0.982 times 10 to the 3. And then you simply shift over the decimal point and you make your magnitude smaller to accommodate this so that you can get back into that scientific notation. So we'll see these concepts sort of come into play later. This is sort of in the wrong place. That's the significant digits, and this is the exponent, but we carry on. Multiplication in scientific notation is also pretty simple. You just have to multiply the significands, and you have to add the you have to add the exponent values together, because 10 to the third times 10 to the minus 2 is just 10 to the 1. So it's basically 10 to the 3 minus 2, which is 10 to the 1. So that's how multiplication works. You might have to shift the decimal point to the right or left, but you won't have to do it by as much as you would have to for addition or subtraction. Alright, so let's talk about binary floating point notation. This is going to make use of 32 bits by the IEEE specification, and we have different segments of these 32 bits representing different things. So we have the sign bit representing positivity versus negativity. It's going to be 0 for positive and 1 for negative, just as was the case for floating point. For 2's complement. And then we have the exponent. The exponent is a 8-bit number, so you have 8 bits for the exponent field, but there's a bias of 127. And the reason why that is because we want to be able to represent small magnitudes in addition to large magnitudes. So by giving a bias of 127, effectively what we're saying is you can have a range of 127 to 128, I believe. So minus 127 to positive 128 exponent value. So 2 to the minus 127 to 2 to the 128th power, which is a super large range of bits. That's huge. And then you have our significand. And note that the significand in scientific notation was going to be some value where you had a decimal point preceded by some digit between between 1 and 9, and only that digit could come before the decimal point. Everything else had to come after the decimal point. With floating point, what we have is we have an implicit 1 right here. So it'll be 1 point, all this stuff. And basically, because we know there's going to be a 1 there, we don't have to encode it, and that saves us space in our actual representation of what it is. So this actual value here is going to be similar to what we had in fixed point binary, where each of these indicates 2 to some negative value. So this bit will correspond to 2 to the minus 1, 2 to the minus 2, all the way to 2 to the minus 23, because we have 23 bits corresponding to this significant field, the F field. And if you sum up these numbers, you get something that's not quite 1, but it's almost 1. And so because we have implicit 1 here, the smallest significand we have is going to be 1. and the largest is going to be something very close to 2. So it's going to be a value between 1 and 2 basically, and this is how I like to express it. But the rationale for this is that if you multiply by some value between 1 and 2, well, you're multiplying that to a power of 2 for the exponent, and so if you do that, you can get between any two values of 2. So if our exponent is 2 to the 3, we can get pretty much any number between 2 to the 3 and 2 to the 4 by multiplying 2 to the 1.23 or 2 to the 1.99. Those will give us values between 2 to the 3 and 2 to the 4, and so as a result, we can get a really large range of numbers. Right here we have an explicit equation that is letting us do this, and we'll look at what it's doing for this value that we have as an example up here. So for the sign bit, a good way of thinking about that is it's going to be minus 1 to the power of whatever the sign bit is. Minus 1 to the 0 is 1, which indicates positivity, and minus 1 to the 1 is going to be negative 1, which indicates negativity. So that'll give you your sign, and you just multiply that negative 1 or positive 1 by everything else, multiplied by 1 times, or 1 point the F field. So we have our implicit 1 in here. We just know it's there. It's not in the representation here, but we know that when we decode it, we have a 1 there. You put your entire F field here, and you end up with some value between 1 and 2. Multiply times 2 to the e minus 127. Minus 127 because you have a bias of 127 built in. So if you had 127 in here, what you would really mean is to the 0th power. And so for this example up here, we'd end up with minus 1 to the 0 times 1.3125. 0.3125 because here we have 2 to the minus 2, here we have 2 to the minus 4, and that gives us 0.25 plus 0.625, or 0.0625. Multiply by 2 to the 5, since in this value up here, we have binary 128 plus 4 is 132, I think. Yeah, so 2 to the 132 minus 127 gives you 2 to the 5th, and if you do all that, you get 42. Here are just some examples of numbers in floating point. For 1, you would have a positive value, so you'd have 0 in the sign bit. 0, we want 0 in the exponent bit, so it would be encoded as 127 in the E field, because you end up subtracting 127. And then you have nothing in the F field, because we have an implicit 1 already. We don't need to add any other fractional values on top of it. And this is all what it is in binary, but you could equivalently express it this way in hex. And you would do the same thing, very similar approach if you want to do the 1/2 or -2. Zeros are represented in a very specific way, where if you applied the formula that we saw on an earlier slide to it, you wouldn't get 0, but we just have taken these numbers to mean 0. And if a compiler is looking at them, it'll know that what we really meant is 0. And what is used to indicate 0 is all zeros in the exponent field and all zeros in the significand field. And you could have either a 0 or a 1 in the sign field. So what this really kind of shows is that this is 0 and -0, but they mean the same thing. We also have different values for infinity. Again, if you applied the actual formula to it, you wouldn't get infinity. You can't get infinity with a formula. But we'll know that this encoded value is meant to be decoded to mean infinity. And basically what we have is if the E field is all 1s and the F field is all 0s, then we know we mean infinity. And we use the sign bit because you could have positive infinity or negative infinity. And there are other numbers in floating point used to represent exceptions or not a number or other special cases, but you won't be expected to know these. But it's important to know that there are special numbers within floating point that the formula doesn't apply to, and it just means something special. We have something else going on here where for numbers that have the E field completely, filled with zeros, we want to have different behavior. We want to be able to have numbers even smaller than 2 to the minus 127, because this gives us extra specificity, I suppose. And the main idea here is that if you have your E field set to zeros, rather than having it mean 2 to the minus 127, what it'll do is it'll look at all of these ones, and it'll multiply by 2 to the minus 126. So, for example, and the F field retains its same values, where this one is 2 to the minus 1, this one's 2 to the minus 23. So you look at what's filled in, and you multiply by 2 to the minus 26. So, in effect, because the E field is set to 0, what we do is we get rid of the hidden 1. It becomes a hidden 0 instead, and this lets us get numbers that are smaller than what was possible before. And you multiply by 2 to the minus 126. So, for example, the smallest number you can get with this is you have 2 to the minus 23rd here, because that bit is set to 1, and it's 0.2 to the minus 23rd this time, instead of 1.2 to the minus 23rd. So what you get is 2 to the minus 23rd times 2 to the minus 126, and that gives you 1 times 2 to the minus 149, which is even smaller than what was possible before. I don't know the exact use of this, but you can do it, and that's pretty cool. The main takeaway is that you can have special representations of information within a well-defined specification. And this is called the denormalized gap. And you should know that floating point is not natural. I'm not going to use an example, but basically because you use such weird stuff with adding fractional parts, and these fractional parts are all powers of 2, you're not going to be able to represent every single number. You'll be able to get close, but not exactly there. To be precise, I think a rule I heard one time is that if it's you represent the decimal number you're trying to express as a fraction, so for example 0.1 would be 1 over 10, you can't represent 1/10 exactly in floating point, because with these fractional bits there's nothing that has that's to the power of 10 or anything similar. But if it's something that ends up being over a power of 2, like 0.25 gives you 1 over 4, you have 2 to the minus 2 as one of your things in the F field, and so that would be possible to obtain. So a good heuristic that you can follow is if you have a value in the denominator that's a power of 2, it will be possible for you to represent it exactly. Otherwise, you can get very close, but not exactly there. And the consequence of this is when you multiply or add specific numbers that aren't powers of 2 exactly, like I just showed you, you're not going to get the exact value. And that's why sometimes you get weird rounding errors and stuff in your calculator, or your thing is a little bit off by some tiny decimal point. Also, floating point arithmetic is not associative, and in some cases addition might not even result in a change. Pretty wild. Now that we've got our ALU with the multiplication and division and the arithmetic, shift, and Boolean operations, we have almost all we need to build an entire MIPS processor, but what we need now is the ability to save state. So we've got two kinds of memory. We've got ROM and we've got RAM. ROM is read-only memory, and that can basically be thought of as a lookup table. Because it's read-only, you can think of it as having certain bytes always in the same memory address and meaning the same thing. So you can think of it as a lookup table where you have a multiplexer, you send in some certain bits indicating that that's what you want to get out, and then based on what your A and B inputs are, you will get a certain output. And you implement ROM as a lookup table using a multiplexer, and that's one way that can work. Now I'll talk about read-write memories, which is RAM. RAM is a little bit different from ROM. It has some parameters that are similar in that you have k address bits, so each memory address is going to have k bits. And you have 2 to the k memory locations, so 2 to the k possible data values. Each data value has n bits, but what's different is you need a control input that specifies reading or writing, and typically only one wire is needed, but sometimes two separate wires are used. And the way that this is implemented is using a latch. And the way that this is done is a extension of our friend from before, the multiplexer. So recall that from a multiplexer, for this selector bit, if you send in a 0, you look at the value of A. If you send in a 1, you look at the value of B. And so what we had before was strictly combinational because it only depended on A and B, but now it depends on the output Y also, because the output Y is going to loop back in and become your new value of A. So basically, if you have 0 as your selector bit for a while, what's going to happen is you're going to have the value that you have for A just continually looping through because it just comes in as the output. You look at that when it's your input and it comes out again, and as long as the selector value is 0, that's what you're going to get. And because you have this feedback path, it's not a combinational circuit anymore, it's going to be sequential. And we call Q our output, and we have these other letters to refer to each of the bits by convention. D represents data, so we said that when we have a 0 coming in the multiplexer, we have the Q value circulating through it, back through itself, preserving its state. But if we look at the 1 bit for our selector, then that's going to be considered our data. And so what data is this is just like any other transistor. You have voltage coming in or out, it's going to be high or low. And you're going to look at it and you're going to be able to send it as an output, and eventually you can have that as the new state once you switch the multiplexer from 1 to 0. And the multiplexer bit, instead of being called S like before, it's now called G for gate. And we have a sort of truth table for this. And what we see is that when G is 0, you get out the value of your Q input. So your Q input is basically this value that you had out, but looping back around. That's why Q in and Q out are the same, is because you just have whatever value you had for Q looping back around. And then if your gate input is 1, you have your D value, which is your data. Data is just some voltage coming in. It can be variable, so it can start out as 1, go down to 0. It just depends on whatever the input is during that time period. And so the state signal that you have is going to be your Q, and it appears as both the input and the output. So Q is called stable when you have 0 for your G for your multiplexer value, because it's just looping around here, and you have Q following D or your data when the multiplexer value is 1. So hopefully that's very clear. Here's an example of how that works. We'll notice that G is going to start off at 0, and so because G is 0, we're going to have a stable Q value here. So Q is just assumed to start off as low, and so there's data coming in, but we're simply ignoring it. But as soon as the gate rises and we have our 0 change to a 1, suddenly we're looking at the data, and note that everything that's going on here ends up getting processed down here. So you're looking at data, and that becomes your Q output. And then once the gate closes, goes from 1 to 0, what happens is we look at what the value of Q was, what the state of Q was right before the gate closes, and that is what's going to be preserved for the entirety of while the gate is closed and Q is stable. Gate opens again, and bam, we're back to copying what's going on in D, looking at D, having that as our state, and then when the gate closes, you copy whatever the state is here. So the main takeaway from this diagram is that when the gate is high, you're simply copying what's going on in D for your output Q, and when the gate is low, you simply hang on to whatever state you had right before the gate switched to low. And this is called a positive latch. You can also have a negative latch, which will do pretty much the same thing, except for we have an inverter here. So when you would have had a 1 before, you would have had a 0 now, and vice versa. And what this ends up doing is, instead of the behavior you have here, you would have G looking like this instead, and you would have to do the appropriate stuff here. So because G would be high here, you would have to have D follow it instead, or you'd have to have Q follow D down here. And so you basically have an inverse behavior where if the gate is closed, we're going to follow D. And if if the gate is closed according to like how we see here, during this time frame we would see D being followed by Q, and in this time period it would be stable. So where you would have had a Q following D before, you will now have a stable period, and where you had a stable period before, you'll now have Q following D. And something that is important to note with these latch timing is the whole reason we have these latches is that we want to hold on to some sort of state in the stable period so that we can then actually do something like some sort of combinational or sequential logic with them. And in order to actually do that, we need to make sure that when we are switching from a high state to a low state, we need to make sure that this input here, this data, is at the value we want it to be when Q is stable for long enough for it to actually be read. So we wouldn't want it to fall all the way back down to 0 right before we are capturing the data and Q is stable, for example. And so the timing specifications that we have here are T-pulse. So this is to guarantee that the G is active for long enough for the latch to capture the data. And we have T-setup. So this means that the D value has to propagate through the feedback path before the latch becomes opaque. And T-setup is the time specification I was just talking about now. T-pulse is ensuring that your multiplexer value, the gate, is open long enough to actually capture those values. And then you have a holding time, which is going to guarantee that the latch is opaque and Q is stable before you let D change again. Alright, so this is good, but something that we can see here is we still have these parts here where we're capturing D, and those are kind of unstable and go up and down. What if we want to make sure that the value of Q is going to be stable for an entire interval of G opening and closing? Well, it turns out that's possible, and we have this sort of analogy using a toll booth. So if we leave the gate open for too long, then you can have multiple values come through it, and that's what you see when you have stuff like this making it into Q during an interval. And in a sort of analogy, you can see this toll booth gate opening and all the cars going through. We want to avoid this behavior. The solution is you have two gates and have only one open at a time, so that the car over here is forced to wait for the other car to make it completely through before it can make its way through. The idea here is that at no time is there an open path between both gates, and we're going to apply the strategy to latches. What this is called is a flip-flop, and what a flip-flop is we have this latch here. Note that this is a negative latch because you have this inverter coming in for the gate, and we have a positive latch here. And note that the output of the original negative latch is going to be your input for the positive latch. So let's just see how this works in practice. And we'll note that this diagram we have on the right is just an abstraction for this sequence of latches that we have here. Something I've had some people ask is, why is this shaped like this? It's because that is inverted. Our approach to this will be to first look at this latch and look at its output, and then take that in as the input to our next latch. So first we'll simply look at what's going on with D, clock, and star. Star being our old value of Q, where Q is our output. note that because this is a negative latch where the clock is low, we're going to have star follow D. And so we can see that here, well, the clock is 0. We have star following what D is doing, and then the clock edge is going to rise, the gate's going to open, and star is going to preserve the value that it had here for this entire interval until the clock goes low again. It's then going to copy D again. So it starts off with getting low to be in the state that D was at the beginning of this interval, follows D, and it's going to stay there when the clock rises, goes from 0 to 1. So when it's 1, it's going to be in its stable state. When the clock is 1, that is, it'll be in its stable state, and then it'll follow D again once it gets out of its stable state and the clock falls. Okay, so now we have the second latch here, and the second latch is just like the first latch, except it's a positive latch, and the input is going to be star instead of D. We're looking at the same clock we had before. Because this is a positive latch, when clock is 0, we're not going to do anything. But when the clock rises, we're going to look at the value of star being our input, and we read in star. Star is going to be positive for this entire time here, or high for this entire time here, rather, because this was its stable period for the negative latch. The stable period for the negative latch is going to be the read-in period for the positive latch. I don't know if I said that backwards, but for the negative latch, this is the stable period, and for the positive latch, this is going to be the read-in period. And so it's going to read in a stable value, and then when the clock falls here and Q itself enters a stable period, you maintain that value. So you end up holding this value for the entire stable and read-in period, which is the desired gate behavior that we saw with the toll booth analogy. And if we keep on following this example, we'll see that when the clock rises, we're going to start looking at values of star again. Star is going to be low during this entire interval, so Q will be low also. And then once the clock falls, we're going to hang on to this value, and so you just keep that low value. And in effect, what this does is it allows you to keep your state for Q within an entire clock cycle between the time a clock rises and between the time the clock rises again. So what the net effect of this is, if you were to just ignore what's happening with star and everything, it would be that when the clock rises, Q is going to look at the value of D, and it's going to keep that value for the entire interval Q. So we saw that for this first clock rise, it preserves that till the next time the clock rises, and here the value of D is low, so it'll be low and hold on to that for a period. Now, so that's a simple heuristic. Well, it's not just a heuristic, it's how flip-flop works, but it's important to know the actual mechanisms behind it with star and how the negative and positive latch come into play, and I hope that example helped you see it. We have more stuff with flip-flop timing. We have propagation delay for the clock and Q. So basically what this means is we need to make sure that we have enough time for the Q value to get copied when we do clock, I believe is what it means. And all the other values have pretty similar definitions to what they did before for the single latch examples. And so the reason we have these flip-flops in the first place is to save state. That's a tongue twister. You want to save the state between a clock cycle, and the idea is you have a flip-flop doing the result of data coming in. You have it saving that data, and you then send that data out of the flip-flop, or rather the data is going to be maintained during the duration of that clock cycle. And during that clock cycle, while the value is stable, you do some sort of combinational logic. It can be a Boolean operation, it can be addition, whatever. And then you take the output from there and you send that into the next flip-flop so that you can then save that new state if that's what it is you want. And so all this happens within the rise and fall of a clock. And that's what we were talking about when we were referring to clock cycles at the very beginning of the class. Now you know what that means. So you can see everything is all coming together now. And we have additional timing constraints here. And we need to make sure that the clock period is greater than or equal to the time it takes to do the flip-flop, the time it takes to do the logic, the combinational logic, and the time it takes to set up the next value. And the reason for that is you need to basically have the value be in its stable state for Q long enough that it'll still be that by the time it's time for the next flip-flop. And if we take the inverse of that, so 1 over that whole expression, you get the clock frequency, so the number of clocks you can have in a particular time period. And I think I'm actually going to stop here for now. The next lecture is the building a computer one, where we use all the pieces that we have so far and actually build a MIPS CPU with them. But this is a kind of hard lecture, and I want to dedicate a little bit more time to it, so we'll finish here. I hope you enjoyed the video, and I hope it was useful to you, and I'll get the next one out as soon as possible.